imaginary power and the I sign. See if it's odd or even, and that's how you see if it's gonna be zero or if you're gonna keep it in an integral.
Well, you could either make the trig part exponential or make the exponential part trig and then use the identities, right? All I remember is we were doing double angle to simplify and for Taylor series.
Okay.
Presentation, we use double angle functions. Wow.
So we are going to move on to the next topic in the course, which is high-level state machines, which will enable us to make more complex systems than just finite state machines allow us to make. The other announcement is homework 4. I did just release it this morning. So it's not going to be due until your quiz in 2 weeks. So there's no quiz next Wednesday, but the Wednesday after you have a quiz. So homework is due before that. The homework is a little bit longer. It is still just one question, but there's just a lot of steps involved with the finite state machines. Okay. So
Class where you gave us.
So it starts with the description of the finite state machine. You need to draw the finite state machine. You need to give the excitation table. Then you need to give the K-maps. From the K-maps, you get the equations. From the equations, you draw the circuit. So it's the whole process. So it's one question, but it's very long. All right. So, like I mentioned, we are going to start high-level state machines today. I don't expect to finish the set of slides today. We'll finish them next week. But why do we need high-level state machines? So some behaviors might be too complex to describe by using just normal finite state machines. Like if we have multi-bit inputs, like here we have A is an 8-bit input, which is the value of the deposited coin, and S is an 8-bit input, which is the cost of the soda. Having all of those things on the transitions of your finite state machine would look very, very messy, right? So it's not practical to use the classical finite state machines for things like this. And the other thing that finite state machines don't offer is like a stored memory. So here we have this 8-bit input S, which is the cost. So we're saying the cost is 50, whether it's 50 cents, something like that. And then if we have A, it's again an 8-bit input. So someone deposited a quarter, right? And then here's our internal storage. So we have this total, which is the total amount of money that the customer has input so far, right? And then if they put in another quarter, we get another input of 25 from A. So our total would increase to 50. Okay. So once we're at 50, that means that we can output D, which is saying that a soda can be dispensed, right? So this is the first poll. Don't answer this yet. I need to deactivate it for the other class. So you can start thinking about this while I get you the code. So your code for today is 801. And I talked a little bit about why we use high-level state machines already. Okay, I think most of you have answered this question. So we're not quite at the threshold. There are two answers that are popular. One of them is right. Well, actually, both of them are right, but one of them is more right. So do talk to each other and see if you can come to more convergence towards the most correct answer.
You know how to make that? What? No, but that's what's supposed to be. Yeah, but try it, right? Everything. I think it's, we can do it. I mean, you can have it. Yeah. Yeah, it's really.
Hey, do change your answer if you were convinced to change. Okay. So we didn't have too much movement. It was like we flip-flop between two.
A decent one?
Oh, yeah? All right, so let's think about these one thing at a time. So 8-bit input outputs. What would that look like on a finite state machine? Draw my transition, like this is my state, this is my other state. I draw my transition. Normally I just have one thing here. But if I have 8-bit inputs, I'm gonna have like A naught, B, C, like I have to write them all out. Okay. And then if I have multiple 8-bit inputs, like here I have S and A, that's not going to look very pretty, right? It's going to be very hard to understand very quickly. So the high level state machine makes this easier. What about tracking the current total? We saw a finite state machine where we were tracking a total before, right? You can do it. Yeah.
The higher the total, the more states you have, depending on how you.
Not just the higher the total, but our example that we went over, we were only inputting of a nickel or a dime.
Yeah, not
right?
the.
But how many different forms of coins do we have in reality? Right? So if even if your vending machine it only costs $1, right? You have to accept pennies. You would have a state for every single cent, right? That finite state machine would look huge in the end, right? It would still be relatively easy to understand what it's doing because you do have this finite amount of inputs because you have what pennies, nickels, dimes, quarters, a 50-cent coin, and $1. But if you want to give change, then there's even more states. And maybe you need to also accept like a $5 bill, right? So keeping track of this total with this stored memory also a lot easier with high level state machines. Right. What about the multi-bit comparison? Can I do a multi-bit comparison in a finite state machine? How?
Well, the one we did in Rad is just a one bit comparison, right?
Yeah, so how do I do multi-bit comparison?
You have to do like multiple finite state machines. Or just
Mm.
more states.
You can do it with more states. It is possible. Every single one of your states would have to correspond to the different combinations though. So this is possible, but just like for the AP input and also keeping track of the total, your finite state machine would look very, very messy. So this makes multi-bit comparison a lot easier because I can just say, is total greater than S as my transition. That's all I have to do in this high-level state machine. So we like A, B, and C. So we like D. All of these reasons are why we use high-level state machines. Right, so here's our high-level state machine with the example of how this is easier. So we have this multi-bit inputs and outputs, right? We have A and S as inputs, and they are both 8 bits long. And then we also have local storage. So we have this total register that keeps track of how much money has been dispensed. And then we have arithmetic operations. When we are in state add, total adds A to the total. Right? We can do that in this high-level state machine. If we wanted to do that in finite state machines, we'd have to transition to another state that represents a different total. Right? So this is what a finite state machine looks like. I mean, a high-level state machine. Here are conventions. So if you have a single bit, you have single quotes. If you have an integer, you have no quotes. If you have multi-bit, you do double quotes. And then we have these comparisons. So we can do equal, equal. And we can also do, like over here, we have less than, and this is greater than, right? So we can do all of these comparisons. And we have arithmetic operations available, like adding. And then the multi-bit outputs, if you had a multi-bit output, should be registered through local storage. And then if you have any comments, you just prepend these double slash, right? So when output is 1, it dispenses a sum. Right? All right, so this is your next question. How does the high-level state machine differ from the finite state machine for this problem? Okay, I don't think anyone is still thinking about this. We are kind of close to the threshold, so we don't have to do the discussion here. So the first statement, the high-level state machine stores multi-bit data, but the finite state machine doesn't. Yes? Yes. We have local storage, right? We can keep track of total this way, rather than with these states that represent different things. The finite state machine stores the states, but the high-level state machine doesn't. Do we have states in the high-level state machine? Yes. And we for sure know that we have states in the finite state machine, so this isn't right, right? And implementing high-level state machine and finite state machine requires these multi-bit data registers. Finite state machines do not have multi-bit data registers. We have single-bit state registers, right? We don't have any way of storing real data. So because we marked those off, this isn't right. And then because we said A, we like it, this isn't right, right? So then let's just take a look at this high-level state machine before we move on. Let me switch to the laser pointer. We first go into the initial state, right? And then in the initial state, we're saying we output for D 0 because we haven't received any money from the customer, right? So we should not dispense a soda. And we reset total to 0. And then no matter what comes on the input, we transition to wait. Right? So if we have an arrow with no condition, we always transition, right? And then in wait, we have these other transitions to go. If we get an input C, so an input C means the customer dispensed the coin, right? Then we go to add. And in add, we do total is total plus A, which was the value of the coin. And then we go back to wait. And then in wait, if we have that total is less than S, which is our cost of the soda, and we don't have a coin, then this should be total is greater than S, not less than. I will fix that later. Great. So this will be my reminder. Total is greater than S. Right, so if total is greater than S and we don't receive any coin, then we should go to the dispense state. And in the dispense state, we output that dispense is 1, right? Because the customer has put in enough money to buy a soda. And after we dispense, we go back to init to reset dispense, reset total, go to wait for the next customer, right? But if we don't receive a coin and total is less than the cost of a soda, then we just continue to wait for a new coin, right? So this is how the high-level state machine works for this soda dispenser. Yeah.
So C is whether or not you input a coin.
Mhm.
S is whatever total
S is the cost of the soda,
the cost is.
so that the owner of it can change the cost.
And then the A is the value of the coin.
A is the value of the coin. Yep. And then total is the total amount of money dispensed so far. But is it clear how this works and how we can have these more complex transitions And because we have these more complex transitions, along with the storage, we can have a smaller amount of states. Right. So what about the similarities between finite state machines and high level state machines? So which of the following are common between them? And again, do answer this on your own first. I don't see anyone changing their answer anymore. I think we are done thinking about this. We're not quite at the threshold, but we are close enough. So we can just go over this together. So do transitions happen at the edge of a clock? So what would be different about the high level state machine? Are we using anything different? Or is it still going to be flip-flops? The transition is still happening on the edge of the clock. Right? We're still using flip-flops. So we like this. That's common. Do they both have external complex data? Input into finite state machines. How many bits has it been? Is that complex data? But for a high level state machine, the first one we're seeing, we have two 8-bit inputs. Okay. That's different, right? And then based on these two, it's not this. And then because we said A, it's not this. So we like A, right? It's just a reminder that we're still using the same underlying hardware. It's going to be flip-flops as our storage. And we're still going to use digital logic equations and circuits to calculate what to do next. But now, instead of just using K-maps, we'll also be using digital logic components in order to calculate things like using an adder to add the total, or using comparisons in order to do this transition properly. Oh wait, this one has a not over it. Okay, I don't need to change it. I didn't see it. All right, so the RTL design process for high-level state machines is going to, again, be capture the behavior with the high-level state machine, and you will convert it to a circuit by creating the high-level architecture, which is going to be two things: the data path and the control path. And for the data path, we have to make sure that the data path can do all of the required high-level state machines data operations. So if we have those comparisons, if we have those adds, if we do any of those kind of operations, our data path needs to support it. And then we design the controller to control the data path so that when it's in this current state, the data flows through the data path in a certain way in order to do the add or not do the add if you're not supposed to. So here is our soda dispenser, and here's our data path. So we have a total register, right? Right here. So we need in our data path an 8-bit register. And when we have a register, it should have these control signals. You need to be able to set it to be enabled with the load, or we should also have this clear, right? To clear it out to 0 to begin with. And the other thing that we need to be able to do is we need to be able to compare S with the total register, right? To see if they have dispensed enough money to pay for the soda, where S is the cost of the soda. So that's why we have this comparison, right? And what we're comparing is total, right? From the total register, along with our input S. And then the other thing that we need to do is from our state machine, we need to be able to add A to total. So one of our inputs to this adder is total. The other input is A. And where does the result go? Back into total. So we connect everything according to the equations from the high-level state machine. Like we are doing this comparison. What are we adding? Where does it go? That defines the connections between these different components. And then the next step is to create the control. So we have all of these control signals, right? Total is less than S, clear, load. Now we need to create the control block in order to process these signals.
So the signal coming out of the comparator is that like a single bit? Like, yes, they match, no, they don't.
It's not matching. It's if total is less than S, that bit is. If total is not less than S, that bit is 0. Because that will give us this, which our control will then use to tell us when we should transition, if we need to transition, right? All right, so this is our next question. According to the current design, under which of the following conditions does the register output total change at the rising clock edge? Yes, starting to see answers change. All right, we're moving towards the right answer. All right, so let's go over this together then. Just again, one by one. Whenever the value of a coin is inserted, does total change? Is that what causes total to change? No. This does not cause total to change. It's a precursor to when we should change total. Whenever the cost of a soda changes? No. When the signal total load becomes high. This will change total, right?
Because that's the transition from wait to add, right? That's the C part, is when the load becomes high. Or,
When we are in add,
oh, you're.
total load will.
Oh.
Well, I'm just talking about from these signals, from the current design, what causes total to change, right? So if we are, and the total load being 1 is what would cause total to change. So then the key is that when we are in add, we need total to change based on the load, right? Because if the load is 1, then we get on the input to total a plus total, right?
Oh.
So we need this. And then when the signal total clear becomes high, this also changes total, right? Because if total clear is 1, total becomes 0, right? It's the clear signal. So that is the case for when we're in, say, init, right? So these are the two things that are going to cause total to change. And we should keep track of for control. Yeah.
So even if you are at a like initial state of total is 0, when the total load signal is high, then that pushes that 0 to activate the 0 plus a adder, and then to feed the.
No, it would just be inside this register. It's a register that has this control of clear. So like in your lab, you made synchronous reset register, asynchronous reset register. The clear is the reset.
Yeah.
So it's an input into the register. It doesn't care what is on the input here. It just makes total 0.
Oh, yeah, but if you're at 0 and then you signal the load to be high, then that will send the 0 to the 8-bit adder so that it adds to the value of the coin and then.
Yeah, so that would be for total load. Yeah. So C and D are what causes total to change, right? So the next step is we need to connect the data path to the controller. So the controller's inputs are going to be the external inputs. So that's going to be C, right? And then we also have these inputs from data path. So we have the comparator output, which is total less than S. And then controller outputs is going to be, we have the external output D, which is to dispense the soda. And then our other outputs are to control that total register. Should it be loading or should it be clearing? Or should it be doing nothing and just hold its current value? So here we're going to create the controller for the high-level state machine. And the controller for the high-level state machine is just a finite state machine. And this finite state machine uses the exact same states as the high level state machine and transitions. But now everything is one bit, right? We converted the comparison into 1 bit because we got it from the data path, right? So we have these 1-bit inputs, and we also have just 1-bit outputs, right? This causes D to become 0, this causes D to be 1. So it is a simple state machine, so it can be implemented with a finite state machine. So all you have to do is copy and paste the high-level state machine and its transitions, and you just have to make sure that you convert all of the comparisons on the edges to be the 1-bit inputs that you get from the data path, right? So here we have total less than S, but we invert it, which means that total is greater than or equal to S. And then we have, if we have a coin or not, so this is no coin, we transition to dispense. And then we also have the same convention as before. If we have a transition with no conditions, we always transition. And if a combination is not shown, you just stay in that state, right? So that is our finite state machine. And if we implement this finite state machine, we can create the controller for the high level state machine. So we would implement this finite state machine exactly the same way that we've done it before, right? We have the design, we can create the excitation table. From the excitation table, we can get the K-maps. K-maps, we get equations. Equations, we can draw the finite state machine. Okay. And then basically all this finite state machine is doing is controlling the data path. Because now when I'm in add, one of my outputs is total load is going to be 1. So that causes total to increment by the input A, right? And if I'm not in add, total load is never 1, right? Because if I'm not in add, I don't want to add A to the total because nothing was input by the customer yet, right? So like I mentioned, you finalize it by, here is my state encoding. This is my input C when a customer inputs a coin. This is my input from the data path, comparing total to the total cost of a soda, which is S. This is my next state. This is my output D to dispense. This is when do I need to load? When do I need to clear? Right? And we can do 1, 2, 3, 4, 5 K-maps to create this finite state machine. Right. So is there any question on this process of how to make a high-level state machine? What's the difference between data path? What's the difference between control? Yeah.
Those RTLs down.
Register transfer level. So register transfer level is just this drawing, which is described by VHDL code. So when you're writing VHDL code, you're creating register transfer level designs. We're all good with this? Yes. S and A are also inputs. So S is the input of how much does the soda cost? and then A is the input from after the coin was dispensed, the machine figured out this is the cost of the coin. Is this process clear though? From the description, create a high-level state machine, which would look something like this. We have inputs, we have outputs, we have storage, and then we have the states and the transitions. Then we need to make it into a circuit. So we first create the data path, which based on the high-level state machine diagram, we use all of the components that we know that we need. Like we needed the adder, we needed the comparator, we needed the register to store total. And the high-level state machine diagram also tells us how these things are connected, right? We need to connect total to one of the inputs of the adder, A to the other, and then the output of the adder goes back into total, things like that. Then we create the controller, and the controller is just the high-level state machine states and transitions copy pasted and converted everything to 1 bit. And we convert everything to 1 bit from the data path. If we need any of those comparisons, it's computed in the data path, and then we get the 1 bit outputs as inputs into the controller. And then once we have that, it's back to what we already know. Right? Yes. The data path. Yes. There would be 3 files. Yeah. So 1 is the data path, right? So you'd create an entity data path. 1 is the finite state machine for the controller. And then the third is top level, connecting them together. And you might have more if you have different designs inside the data path, like the adder. But for this class, you will mostly be able to do everything you need for the data path with behavioral coding. Like for the adder, you already saw for the counter, you can just do, if you import the package math, you can do counter is counter plus 1. So the same thing, you can do that. You would be able to do total is total plus A. So for the most part, you don't have to do these sub-designs. And if you need a mux is just an if statement, right? So for the next lab, you will be creating a high-level state machine. So you will do, and it says in the instructions, you will create these 3 separate files. And it's a suggestion, again, you don't have to create these 3 separate files. You can do it in 1 file. You can do it in 1 big process block, but it is just not recommended. Yeah, except it wouldn't be a counter, it would just be an adder. And then if you look at the data path, just like if you looked at the data path for the counter, it instantiates an adder.
Sorry.
Yeah, for the total. Yeah. Yeah. So all of these signals, you would determine what signal that you would need. Do I need to be able to clear? Do I need to be able to load? if it's always enabled, I don't really need to have a enable, right? But almost certainly I always need a clear, because if I don't have a clear, it's junk in the beginning, right? Okay, so I'm gonna save this one for next time with the high level state machine in order to implement this distance measure. And I will stick around here if you have more questions about high level state machines. The only other thing I wanted to say is next week's lab is the hardest lab with the, oh wait, not next week. Next week you have, you're doing procedures and functions. So 2 weeks from now, when you do the high level state machine, which is the memory lab, that one's going to be the hardest. And next week's lab is one of the easiest, procedures and functions. So the idea is that you finish next week's lab very quickly, and you have time during that week to start and begin working on the high level state machine memory lab. And your final project will be very similar to the memory lab. You can almost copy paste 80% of what you worked on for the memory lab for the final project. So it is very critical that you spend time, get the memory lab right. Okay. So again, I'll stay here. We can walk to my office. I'll be here for questions.